This of interest. What I've done is set up a model, a very simple model, where I've created a rotational path. Basically, this is a looking at top-down view, overhead view. This is a cylinder or a circle that rotates in this direction, counterclockwise as you look at it. The center of the rotation is here, where the arrow is. Pinned to the outside of that circle, cylinder, if you will, is a rod. This rod, and if you look at the measurement units, this is accurate. These represent feet. So what we have is a radius, a cylinder with a radius of about 2 feet, and we have a rod that's about 3 feet in length. And the rod has been selected with a mass of about 2 pounds, a little under 2 pounds, 0.9, a little under 2 pounds. And what I've done also is create a rotational speed equal to what a high-level hitter can do from a standpoint of going from here, rotating the circle, to here. The time divisions that I'm using is synchronized to frames on VCR. So what I've done is set this up so that the length of time it takes to rotate around this perimeter, to pull this rod essentially, move this rod around this outside perimeter, is equal to the length of time it takes a Major League player, high-level player, to rotate once they've made their decision they're going to swing. This is a free-moving pin, so that this rod can move either way under the influence of the rotation. Over here, I've created readouts. Total force, the force is in the direction of, if you look at this, force in the x direction, this is the x-axis here. You see the x-axis here, y-axis here, positive x, positive y, negative y. As this rotates, this tip will move, and you can read the forces, this rod will move around, but also it will be under the influence of this pin. This pin will be pulling it due to the rotation of the cylinder, circle. And we can measure the forces in the x direction, y direction, and the resultant, in other words, the resultant force along the length of the rod, but in this case the bat simulation. Set it up so that I can measure tip speed, again, same thing, in the velocity in the x direction, positive, negative, y direction, and the resultant, the actual velocity, speed, not velocity. Also the torque, the rotational torque on that the rod is creating, the bat is creating as it's moved along this circle. And then we have the time readout. So what I'm going to do is advance this, and each click represents 1 frame on a VCR. That's the way I set the timing, so that you can look at Major League players, and Major League players will execute their swing in anywhere from 6 to 7 frames once they start rotating to swing. Again, this rod is free to move, so I'm going to advance it 1 click at a time. You can see that as I'm moving it, the natural tendency, because of the rotation, is for the rod to start to move into it, but also you have a force acting out also which wants to pull it out. And again, this is free constraint. You can measure the force that I'm actually exerting on the rod due to the rotation and the force. And I'm going to just pause this for a minute. I paused it for a minute because I wanted to make sure the value of the weight of the bat. The weight of the bat is about a little under 2 pounds, 1.8 pounds, which is approximately 31 or 32 ounces. So this is about 34 inches long and about 33 ounces. So as I move this, there will be a force acting along, and the force is measured here, 20 pounds. In other words, a pulling force of 20 pounds. There's a rotational torque of 8 pounds. In other words, there's a rotational torque that wants to move inward to close the circle down. Again, this is positive as you're pulling of 8 foot-pounds, which is not very much. And I'll click it again. Oops, I'll click it again. And I've got to this point, and the force here is up to 50 pounds The tip speed is now 51 miles an hour. Tip speed being the speed here, 51 miles an hour. And the torque is about 8 foot-pounds. 8 pounds over 1 foot. Not very much torque. And that's a torque due to the change in direction. I mean, that's not torque that I'm putting on with the pin here. It's just torque due to the change in direction of the mass of the bat. As I reach this point, and this is a fairly, believe it or not, this is a fairly accurate, if you look at the top view, this is a pretty accurate representation of what actually happens when you swing the bat. My tip speed is now 72 miles an hour, and my force along the bat is 92 pounds, and my torque is still 8 pounds. And I would expect that to stay reasonably, you know, it's going to decrease. And the reason why there's torque is because of the mass of the bat wanting to move outward due to the pulling action, centripetal force, look at it, moving. So I have a tip speed of 72 miles an hour. I'll go one more click. And this would be, this next one would be basically at the point of contact. Bang. And I have a tip speed of 88 miles an hour with a force along the bat of 131 pounds and a torque of 3.815 foot-pounds, less than 3, I mean, almost negligible torque. So there's essentially no torque going on here, but there is a tremendous, there's 131 pounds of force along the length of the bat. Again, that's because I'm holding on for dear life, trying to change the direction of the bat. And I'll go one more click. And at this point, the velocity is starting to decrease. It's 89 miles an hour, 132 pounds, and the torque is now negative. It's gone in the negative direction because you can see the swing here with respect to the center of rotation. This is, as I said, I'll go back and click it through, and I'll actually set it up so that, let's see if I can do this. Appearance. Oops. Window appearance, and let's track. Oh, my track. Okay, track. And go here, and track every. Right. Now I'm going to do the same thing. I'm going to click it again, advance it, but I'm going to track the frames so you can see what's going on here. So that, if you go to the physics of baseball, Adair's, this is similar to what you see, except he has more of a elongated, again, this is perfect rotation. Later on, I'll demonstrate some other things, but this, when I say perfect rotation, this is perfect rotation of center with a radius of 2 feet. And 2 feet was chosen because I took that as an average distance with the hands from the center of the body on a pitch. So you can see that just pure rotation, if you maintain this curvature, will generate a tip speed of 90 miles an hour in a typical just turning on the ball. I hope you find this of interest, and I'll have some more goodies as we go along.